So this is the second part of section 6.1.6, more equations and applications. So in the last part, we talked about polynomials and rational equations. In this section, we're going to look at square roots and equations that have exponents in them. So we'll start with the first example here in a second. So our objectives in this particular case is solving radical equations and equations with rational exponents, and then going back and solving equations in quadratic form that are not exactly quadratic in nature. So our third objective in this section is solving radical equations and equations with rational exponents. So our first example is example 5. Here we have the square root of x minus 1 plus 3 is equal to x. So the idea is to isolate, the strategy is to isolate the square root on one side of the equation and then square both sides. Sometimes we have to do it twice if we have more than one square root. So in this example, we have the square root of x minus 1, we've isolated it, is equal to x minus 3. We subtracted 3 from both sides of the equation. And so this is the first equation we did. The second equation then is we square both sides. Here's where we squared both sides, and we get x minus 1 is equal to x minus 3 squared. Now we expand the left side of the equation, and we get x squared minus 6x plus 9 on the left side, and we still have x minus 1. We'll use the zero principle to set up our quadratic equation. So 0 is equal to x squared minus 7x plus 10, and now we factor that particular quadratic, which is x minus 5 times x minus 2. And of course we get the solution x is equal to 5, x is equal to 2. But we need to check our answer. So when we put into 5 into our answer, we get the square root of 5 minus 1 plus 3 is equal to 5. Certainly the square root of 4 plus 3 equals 5, and 2 plus 3 is equal to 5. That checks out. So x equals 5 is okay. When we put in x equals 2, we get the square root of 2 minus 1 plus 3, which when we set up the equation is supposed to equal 2. The square root of 1 plus 3 does not equal 2 because 1 plus 3 doesn't equal 2, it equals 4. So 2 doesn't work in this case, so the only solution here is x is equal to 5. In our practice skill 5, we have a similar equation. The square root of t plus 7 is equal to t minus 5. Well, we're going to square both sides of the equation. And when we do that, we get this equation here. T plus 7 is equal to the square of t minus 5, or the square of t minus 5. Then t plus 7 is equal to the expanded of t minus 5 squared, which is t squared minus 10t plus 25. Now we use the zero principle. We bring the t and the 7 over to the left-hand side of the equation. We get 0 is equal to t squared minus 11t plus 18. Well, this quadratic is factorable. It's factorable into t minus 9 times t minus 2. And again, we get t is equal to 9, t is equal to 2. We check out our results to the following. When we put 9 in, we get the square root of 9 plus 7 is equal to 9 minus 5. So the square root of 16 is equal to 4. That is true, and that checks out. When we put 2 in, however, we get the square root of 2 plus 7 is equal to 2 minus 5. The square root of 9, well, the positive square root of 9 obviously is 3, and 3 doesn't equal negative 3. So the only solution here is t is equal to 9. Now we have 2 square roots. So whenever we have 2 square roots, chances are good that we'll have to do the squaring process twice. And so the first go around, we have isolated one of the square roots on one side of the equation. And so we square both sides of the equation. On the left-hand side, we get 1 minus 2x is equal to, on the right-hand side, the square of 2 plus the square root of 1 minus x squared. When we expand that term on the right-hand side, you have to be careful when you FOIL. So that's something that we have to learn to do very carefully. The left-hand side of the equation stays the same, but the right-hand side of the equation, when we expand it, turns out to be 4 plus 4 times the square root of 1 minus x plus 1 minus x. So we're going to do some combining of like terms. The first time around is not going to be much because we're going to have 1 minus 2x is equal to 5 minus x plus 4 times the square root of 1 minus x. So we're going to isolate the square root again, and when we do that, we bring the 5 minus x over to the left-hand side of the equation, and we get a minus 4 minus x is equal to 4 times the square root of 1 minus x. Now we square again both sides of the equation. You'll notice I pulled out a negative, and we added 4 plus x. But when we square a negative, it's always going to be a positive on the left-hand side of the equation. So when we do the squaring, we get x squared plus 8x plus 16 is equal to 16 times 1 minus x. When we distribute the 16 on the right-hand side, we get 16 minus 16x. And you'll notice that the 16s cancel out. And using the zero principle, we'll bring the negative 16 over to the left-hand side. We get x squared plus 24x is equal to 0. So now I can factor out an x, and we get an x times x plus 24 is equal to 0. So that gives us the factors x equals 0, x equals a negative 24. When we check out the negative 24, it works. It ends up that 7 equals 7, so it works. But when we put 0 in, we end up with a contradiction. We get 1 is not equal to 3. So the only solution here is x is equal to a negative 24. So in practice skill 6, we again have 2 square roots in the equation. And our first step, of course, since we've isolated one of the square roots, we can square both sides of the equation. Again, when we do this, we have to be careful when we FOIL. So when we do FOIL, on the left-hand side we get 1 plus 2 times the square root of n plus 4 plus n plus 4 is equal to 3n plus 1. So now, again, we're going to start combining terms. We get 5 plus n plus 2 times the square root of n plus 4 is equal to 3n plus 1. So we want to isolate the square root on one side of the equation. which we're doing here. So we have 2 times the square root of n plus 4. We bring the other terms over to the right-hand side, and that's equal to 2n minus 4. Now we can divide both sides by 2, which is an easy thing to do, and we end up with the square root of n plus 4 is equal to n minus 2. And now we square both sides again, and we expand, and we get n plus 4 is equal to n squared minus 4n plus 4. The 4's cancel. We can bring the n over and go to the 0 principle, and we get 0 is equal to n squared minus 5n. We can pull out an n. 0 is equal to n times n minus 5. And so our solution at this point is n equals 0, n equals 5. But we need to check. So if we put 5 into, or if we put 0 into the equation first, we get 1 plus the square root of 4 is equal to the square root of 1, and we can see that that's not going to work because 4 does not equal 1. And so 0 does not n is not equal to 0. In the second case, when we put 5 in, we get 1 plus the square root of 5 plus 4 is equal to the square root of 5 times, or 3 times 5 plus 1. So 1 plus the square root of 9 is equal to the square root of 16. This works out because 1 plus 3 is equal to 4, so our solution is n is equal to 5. So now we're dealing with exponents in our equations, and you will recall that for a raised to the 1/nth power is equal to b, if we take the nth power of both sides, we get a is equal to b raised to the n. Also, for a is raised to the nth power equals b, we can take the nth root of both sides of the equation, and we get a is equal to the nth root of b. So in this particular case, we are going to take we're going to cube both sides of the equation, and when we do that, we end up with x squared is equal to 64. Now we take the square root of both sides of the equation, and we see that x is equal to plus or minus the square root of 64, where x is equal to plus or minus 8. And when we do the checking, we see that both 8 and minus 8 work in this particular equation. In practice skill 7, we have two equations that have exponents in the equations. So for part A, we divide first by 2, and we get t minus 3 raised to the 5/6 power is equal to 5. We take the 6th power of both sides of the equation, and we get t minus 3 raised to the 5th power is equal to 5 raised to the 6th power. And now when we take the 5th root of both sides, we get t minus 3 is equal to the 5th root of 5 raised to the 6th power. And we see that this is t is equal to 3 plus 5 raised to the 5th root of 5. For b, m to the 4th is equal to 1 over 16 to the 5th. What we did is we took the 5th power of both sides of the equation. And in the second part of this equation, I'm writing 16 as a factor of a prime 2, so 2 raised to the 4th power. So m to the 4th is equal to 1 over 2 to the 4th raised to the 5th power. Well, when we do the exponent, 1 to the 5th power times 2 to the 4th raised to the 5th power, we get m to the 4th is equal to 1 over 2 to the 20th power. And now we're going to take the fourth root of both sides of the equation. We get m is equal to the fourth root of 1 over the 20th power. And when we do that, we get m is equal to 1 over the 2 to the 5th power, which is just 1 over 32. So in practice skill 8, we're going to use the exponents in doing some of the problems. So suppose that $P in principal is invested in an account that earns compound interest annually and grows to $A in T years. The annual interest rate is given by R is equal to A over P raised to the 1T minus 1. Determine the annual interest rate if $2,000 grows to $2,375.37 after 5 years. When we plug the information into the equation, we get R is equal to 2375.37 divided by 2,000 raised to the 1/5 power minus 1. When we do this on our calculator, we get R is equal to 1.034999 so forth minus 1, which means that R is approximately equal to 0.035, or in our case it would be 3.5% annual interest. In part B, we have to solve the equation to get the answer that we get for A. So if we're solving for A, when you do the algebra, you'll see that A is equal to P times parentheses 1 plus R raised to the T. So now it says if $5,000 is invested at 5%, determine the amount in the account after 6 years. We put in 5,000 for P. We put in 0.05 for 5%. And we put in for T 6. When we do the calculation, 5,000 parentheses 1.05 raised to the 6th power, we get approximately $6,700.48. Objective 4. Solve equations in quadratic form. So our first example, 10, is a quadratic type of equation. So we're going to use substitution to solve a problem like this. So we have x to the 4th minus 3x squared minus 4 is equal to 0. And we let a equal x squared. So that's our substitution method. So now when we let a equal x squared, we get ax squared minus 3a minus 4 equals 0. We see that that factors into two pieces. A minus 4 times a plus 1 is equal to 0. So a is equal to 4 and a is equal to a minus 1. Now we substitute back for a. We let x squared equal 4 or x squared equal a minus 1. And when we solve for x, we have x is plus or minus the square root of 4, or x is equal to plus or minus 2. For the minus 1, we have x is equal to plus or minus the square root of negative 1, which is I. So x is equal to plus or minus I. And so our solutions are 2, minus 2, I, and minus 1. So you want to check to see if these answers work. You can pause and let to see if they work, and they should. In example 11, we have a fractional exponent type of equation. And again, it looks like it's a quadratic type. And so in this case, we're going to let y equal x to the 1/3 power. When we do that, we can set the equation as y squared minus 3y minus 4 is equal to 0. We notice that that is factorable into two pieces. Y minus 4 times y plus 1. So we have y is equal to 4, y is equal to a minus 1. Now we substitute back in for x to the 1/3 power. So we have x to the 1/3 is equal to 4, or x to the 1/3 is equal to minus 1. Now we cube both sides of the equation and we get x is equal to 4 raised to the 3rd power, or x is equal to a minus 1 raised to the 3rd power. X is equal to 64, or x is equal to minus 1. When we check, we see that both answers work. You can pause and make sure that you see that these will work out, but they both work out, and you can check them on your own. So x is equal to 64 and x is equal to -1. So in example 12, we have exponents that are in the negative exponents. So now we're going to substitute, let b is equal to a x to the minus 1 power. So now we have 2b squared minus 7b plus 6 is equal to 0. We see again that this is factorable into two factors. 2b minus 3 times b minus 2 is equal to 0. b is equal to 3/2, or b is equal to 2. Now we substitute back in. X to the -1 power is 1 over x is equal to 3/2. So this means that x is equal to 2/3 when we do the algebra, or 1 over x is equal to 2, or x is equal to 1/2. Again, when we check our answers, both answers work out. In example 13, now we have an expression that looks like it's a quadratic. 1 minus 3 over x to the squared minus 7 to the parentheses 1 minus 3 over x plus 10 equals 0. We let a equal 1 minus 3 over x. We plug it into the equation and we get a squared minus 7a plus 10 is equal to 0. This again is factorable. We get a minus 5 times a minus 2 is equal to 0. We get a is equal to 5, a is equal to 2. Now we plug in for a, and we see that we get two possibilities. 1 minus 3 over x is equal to 5, or 1 minus 3 over x is equal to 2. When we solve these problems, we get x is equal to a -3/4, or x is equal to a minus 3. Again, we can check the answers, but both answers check out. In some cases, it's better just to expand the terms. So in the case of skill practice number 9, we have the situation where we have the expression x squared minus 6 squared plus 33 x squared minus 6 is plus 62 is equal to 0. We go ahead and we expand the terms, and here we have the terms expanded. X to the 4th minus 12x squared plus 36 plus 33 x squared minus 198 plus 62 is equal to 0. And then, of course, we have, when we combine like terms, we get x to the fourth plus 21x squared minus 100 is equal to 0. Now here we could have done something differently. And in fact, we could have said, okay, let y equal x squared, and then we have y squared minus 21y minus 100 is equal to 0. Oh, this is plus, by the way. That's one of the reasons I made a mistake over on the other side. So here we get y plus 25 times y minus 4 is equal to 0. So y is equal to a minus 25, or y is equal to 4. Now, we substitute back in. We get x squared is equal to a negative 25, or x squared is equal to 4. So x is equal to plus or minus the square root of a negative 25, or x is equal to plus or minus the square root of 4. X is equal to plus or minus 5i, or x is equal to plus or minus 2. So the answer is, these are not the correct answer, but we could have gotten the answer on this side as well. Okay, so in practice skill 10, we have an exponent type of equation. 2 to the t to the 2/3 is equal to 15 minus 7 t to the 1/3. And we're going to use the zero principle to get it into this form. T to the 2/3 plus 7 t to the 1/3 minus 15 is equal to 0. Now we're going to again let a equal t to the 1/3. So now we have 2a squared plus 7a minus 15 is equal to 0. That is factorable. And there's our factors, 2a minus 3 times a plus 5. A is equal to 3/2. A equals minus 5. Now we substitute back in for t to the 1/3 power. And we get t to the 1/3 is equal to 3/2. We cube both sides and we end up with t is equal to 27/8. When we let t is equal to t to the 1/3 is equal to a negative 5, we cube both sides and we get 10 is equal to a negative 125. So our solution here is t is equal to 27/8, or t is equal to a negative 125. So in this example, we're solving for a. We squared both sides of the equation. We get c squared is equal to a squared plus 4. And now we're solving for a, so we isolate a squared on one side of the equation, and we subtract 4 from both sides, and now we take the square root of both sides and we get the plus or minus the square root of c squared minus 4 is equal to a. So there's our answer there for example 15. So in our application problem, Kibler's law gives a relationship between an animal's metabolic rate, mr, and its body mass, m. mr is equal to 73.3 m to the 3/4 power, where mr is measured in kilocalories per day and m is the weight in kilograms. It says find the metabolic rate of a lab mouse weighing 0.02 kilograms, round to the nearest whole unit. Okay, and so we put the answer in and we crunch the numbers on our calculator and we get approximately 3.898 kilograms. And if we round to the whole nearest unit, it's approximately 4 kilograms. Now in part B of example 17, it says find the metabolic rate of an African elephant weighing 3,000 kilograms. Round to the nearest whole unit. So in this case, the mr is equal to 73.3, 3,000 raised to the 3/4 power. When we do this in our calculator, we get the metabolic rate is 29,712 calories, 0.89. So that's approximately 29,713 kilocalories, I believe, is the metabolic rate of an elephant. They have to eat a lot, obviously. In our final example, it asks what is the mass of a house cat that has a metabolic rate of 245 kilocalories per day. Round your answer to the nearest unit. So as you can see, we're trying to solve for m. So 245 is equal to 73.3 times m raised to the 3/4 power. We divide both sides by 73.3 is equal to m raised to the 3/4 power. We raise both sides of the equation to the 4th power, and we get 240, and then we take the cube root of both sides, and we get m is equal to 245 divided by 73.3 to the 4/3, and we get m is approximately 4.997 kilograms, or m is approximately equal to 5 kilograms. And that concludes our chapter 1.6. Please continue to work some of the problems in the book, and we will work some more problems in class.